Dynamic programming is an optimization of recursion. In recursion, you would break a problem down to its base case and solve each sub-problem, building up to the solution to the original problem. Dynamic programming works much like this, so if you understand recursion, you're already most of the way there to understanding it. The big difference between recursion and dynamic programming is that dynamic programming has a time-space trade-off, which means that we use more memory in order to save time. The main requirement for us to be able to use dynamic programming effectively is that the sub-problems that the problem is broken down into need to overlap. Then, instead of solving each sub-problem individually like you would in recursion, you solve each unique sub-problem exactly one time and store the result in an array. Then, when you come across that sub-problem again, you can use the result from the array instead of recomputing it. So we're using the stored solutions of sub-problems to build up to the solution to the original problem. There are two types of dynamic programming: the top-down approach, also known as memoization, and the bottom-up approach, also known as tabulation. Starting with a top-down approach, create an array to store the results of the sub-problems, and then define the original problem in terms of a recursive function that breaks it down into smaller sub-problems. Before you solve each sub-problem, you check the array to see if its result is stored there. If it is, you return the result in order to avoid redundant calculations. Otherwise, compute its result, store that in an array for future use, and then return it. The bottom-up approach works in the opposite way and avoids recursion entirely. It starts at the smallest subproblems, solving them systematically, then building up to the solution of the overall problem. We start by breaking down the main problem into smaller subproblems that can be solved incrementally. We solve these iteratively, using the solutions of the previous subproblems to do so, and storing each new result in the array. We use the results stored in the array to solve larger and larger subproblems until the solution to the original problem has been computed. Let's take a look at an example using both the top-down and bottom-up approach. We'll use the example of Fibonacci numbers. So that you can truly appreciate dynamic programming, we'll start by quickly going through how we can compute this problem using plain recursion. Say we want to compute the fifth Fibonacci number, so f of 5. Well, we do this using the calculation f of 5 equals f of 4 plus f of 3. But that means that to compute f of 5, we also need to know the solutions to both f of 4 and f of 3. But to compute f of 4, we need to know f of 3 and f of 2. And to calculate f of 3, we need to know f of 2 and f of 1, and so on until every root of the tree is a base case. The base cases are f of 1 equals 1 and f of 0 equals 0. We can then use the equation f of n equals f of n minus 1 plus f of n minus 2 to work our way back up the tree to get to the solution to f of 5, which we can see is 5. As you can see, this isn't very efficient. There are so many repeated calculations, and this just gets worse and worse the larger the value of n gets. Dynamic programming is going to fix this. Starting with a top-down approach, we start by checking if f of n, so f of 5, is already in the array. So this approach actually becomes more efficient after you've run the algorithm once. What I mean by that is if you've previously calculated f of 6, then your array will already store values from f of 0 to f of 6. So now when we run f of 5, that value will already be in the array. So all the algorithm needs to do is return that value without needing to do any other calculations. However, if we haven't run f of 6 and we can't find f of 5 in the array, then we check the other values until we reach the base cases. We know that f of 1 equals 1 and f of 0 equals 0, so we store these values in our array. Then we move up to solve f of 2. That's not in the array, so we run the calculation and get f of 2 equals 1, then store this value in the array. We then get to f of 3, and this isn't in the array, so we calculate this as well, giving us 2. Then we get to f of 4, which isn't in the array, and to solve this, we need to know the value of f of 2. In the naive recursion approach, this would have had to be recalculated. However, in the top-down approach, the value of f of 2 is already stored in the array, so we can just return that to use in the calculation of f of 4. We then calculate f of 4 to be 3 and store that in the array. We get to f of 5, and to calculate that, we need to know the values of f of 3 and f of 2. However, these values are already stored in the array, so we can return these. So for each step, we can just use previously stored values until we calculate and return f of 5. Moving on to the bottom-up approach, and as it says in the name, we start at the bottom with the base cases. We initialize an array, which we'll call f, and then initialize the value at index 0 to be 0 and the value at index 1 to be 1, representing the base cases. We'll then populate each cell of the array until we reach the value of n, so in our case 5, using the equation fi equals fi minus 1 plus fi minus 2. So for f at index 2, we would do f1 plus f0, which would be 1 plus 0, so we would get f2 equals 1. So we would get f at index 2 equals 1. Now that we have a value for f at index 2, we can use it to calculate f at index 3, which we can use to calculate f at index 4, and finally f at index 5. Now we have a solution for f at index n, so we stop here and return our result. To summarise, dynamic programming is an optimization of recursion, which involves trading space for time. So instead of recomputing values to subproblems, we calculate their values once, store them, and then reuse them when we need them again later. There are two types of dynamic programming, the top-down approach and the bottom-up approach. If you have any questions, drop them in the comments and I'll get back to you as soon as possible. Don't forget to subscribe if you want to learn more about computer science. I'll see you there. Thanks for watching.